Okay, so here's the homework from the other night. So today we're talking about going through almost a full test here, or interval, I should say, an interval for means. So let's see what happens. So first thing we need to know is standard error. So remember, standard error is basically standard deviation. It's typical deviation or variation from the mean. But oftentimes, especially with the interval, we don't really know the true standard deviation, sigma, for the parameter, but we do know the sample standard deviation, which is called Sx. So to find the standard error, we use Sx instead of sigma. We don't know the parameter, so we use the sample standard deviation called S sub x, and so we use that to get the standard error. But with means, a different formula than proportions. Proportions was square root of PQ over n. Here it's the standard deviation of the sample divided by square root of n. So here's the formula for calculating an interval for means. So it's just a one sample t interval is what we would call this. Notice we start with the statistic. It's x bar. That's our sample mean that we get. So we're not talking about proportions. We're talking about means. Instead of plus or minus z star, it's plus or minus t star. We talked about how to get that using the degrees of freedom. Remember, degrees of freedom is n minus 1. And then you multiply that by the standard error. Okay, here's what the formula sheet has. So to create that interval using your formula sheet, you have to know a little bit of stats. So it says statistic, well, that's your x bar. Critical value, because we're talking about means, it's t star, not z star. And standard error, that formula there is actually at the bottom on your formula sheet. So you don't have to memorize that part. But that's the generic, that's what you get on the formula sheet. You have to create your interval from that basic knowledge. So once you verified, I think we already verified the conditions for the engagement ring. So they give us some numbers. I like this. So after adjusting for inflation, the mean cost of engagement rings is, for a random sample of 1,640, so that's quite a few folks, it was 3,329. This is kind of surprising. Well, not that surprising. Standard deviation is huge. So it's actually bigger than the actual mean there. So standard deviation is 4,739. That means there's a lot of variation in how much people spend to buy rings. Some people don't spend that much, and some people spend quite a bit. So calculate a 99% confidence interval for the means. So to do that, we're going to, first, it's a good idea. I like you writing degrees of freedom on your paper. Degrees of freedom, 1640 minus 1 is 1639. You use it. It's helpful. I've seen a rubric where it requires degrees of freedom, so it's really nice to put that on there somewhere on your paper. So we have to calculate the t star value, right? So to do that, you could kind of draw a curve. This is what I do anyway. Put 0.99, and then this would be 0.005. So to find the t star value right there, you do the inverse t command, 0.995, and that will give you, and you have to put the degrees of freedom. So in this case, it'd be 1639. Because each curve is slightly different depending on the degrees of freedom there. That's 0.995. It's a really bad 5 right there. And so you type that in your calculator and you should get an answer. I think the answer will be negative 2.579. To get to inverse t, if you don't know where that is, menu 6.5 is my guess. Inverse t, there it is. And so then you'd be 0.995. 1639, and it gives you that 2.57 number. Now notice that's very close to, I don't know if you remember, but well, let me do it. So if you go to inverse norm, so if I just did inverse, I'm just going to change the t to norm there. Oh wait, inverse norm, if I take away the degrees of freedom, because there is no such thing there, look at that. Those numbers are really, really close. So you can see you've got this number here and that number there. Those numbers are extremely close. That's because, again, as the degrees of freedom gets larger, it's going to become more and more normal. So it's pretty close to normal. At degrees of freedom of 1639, it's basically a normal curve at that point rather than a t curve. I mean, it is a t curve, but it's so similar to the normal curve. So then we plug in the numbers, right? So for this one, you would plug in. So you'd have 16, I think 3329 was the mean, plus or minus the t critical value is 2.579 times, I think it's standard deviation, which was 4739, over square root of n, which was 1640. So then you type that in your calculator to get the interval, and it gives you that as your interval. Now, of course, there is a way to do this all on your calculator. In fact, I highly recommend, I like you, when you're first learning this, definitely do that. Type it in, get it. Then always double check. I can tell from your test, some of you are not double checking your work, and you double check by doing this. Menu 6, let's see, this is the interval, so it's 6, and this is a t interval. So this one, you go to t interval for one sample t interval is what this is called. Data or stats? This one I think is stats. So if you give you like a list of numbers, that's going to be data. So we're going to stats. X bar is 3329. Standard deviation 4739. It's pretty easy to type this in. N is 1640. Wow, this is easy. You do have to put the confidence level, which in this case 0.99. It just does it all for you, right? So it gives 3027.2. Yeah, that looks good. 3730.8. That looks good. Gives you the margin of error. It gives you the degree of freedom if you're not sure how to calculate that. That's actually really handy, especially as we get into tougher stuff later on. So really, really nice. You can do that in your calculator. Okay, so one sample t interval for means is the confidence interval used to estimate. So that's the name of it. It's called a one sample t interval. So let's talk about, just do another example here. Manufacturer of high resolution video screens must control the tension of the mesh of fine wires that lies behind the surface of the screen. Too much tension will tear the mesh, too little will allow wrinkles. Tension is measured with an electronic device with output readings in millivolts. Some variation is inherent in the production process. The table gives the tension readings for a random sample of 20 screens in a single day's production. So I picture this almost like the tension when you string your racket in tennis or something. It's some kind of machine that's measuring the tension level of the screen, how tight it is in there. So you get all this data. So this one's data. We haven't done this kind. So this is, we're going to use data to do this one. So construct and interpret a 90% confidence interval for the mean tension of all screens produced that day. So first you want to start with, what is the parameter you're studying? So you may be so used to what we've been doing, you may start writing P and you don't write P here. It is not what it is. Mu is the true mean what? And then you're just going to say it in words. Tension of the screens measured in millivolts at this company. And then so you're going to state, so the confidence level is 0.9. And then you're going to start the conditions. So does it say something about random sample there? Maybe I missed something. Does it say something about random sample? So they said state 90% confident mean is the true mean tension of all video screens produced this day. So name what it is. Did it say random sample? Did I miss that? Man, so a random sample. I finally saw it. Random sample of 20 screens. So random sample of 20 screens. So we have random sample. Sorry, I just couldn't see it. I kept looking for it and it wasn't there, of 20 screens. Okay. So now less than 10%. So 20 is less than 10% of all screens produced that day. That seems reasonable. And now we have to do the large sample condition. So there's really three ways to prove large samples. So one, you need one of three. You don't need all three. In fact, you rarely get all three. So one is the population is normal. Well, it doesn't say anything about the population, so we have no idea. So population normal, we just don't know. The second reason, usually the best reason, is 20, that's the sample size, bigger than or equal to 30. If it's at least 30, no. So these we just don't know. Those are no's. So now the only option is you actually have to show the graph. When I say show the graph, you actually have to draw a graph of this. It could be a dot plot or a histogram. Dot plots are usually easiest, which means you probably need to put this in your calculator, right? So let's actually put this data into our calculator and do it that way. So it's going to take a minute here. I'm going to type this in. So go to Home, Listen Spreadsheet. I'm going to call mine tension. Oops, tension. And I'll start typing the data in 269.5. And I'm going to stop it for a second while I type it in. Okay, so I just typed in all the data. Make sure that you put that last piece of data in there and that there's 20 pieces of data, because at least I have the right number of them. Hopefully I typed them all in correctly. Let's go to Data Statistics and click Tension, and it should graph it for us. So you will almost do like an exact copy of that graph onto your paper. It doesn't have to be perfect, if that makes sense. So, and by the way, what we're looking for here, we're not looking for it to be approximately normal. We're looking for it to be no outliers and no major skewness, right? So looks roughly symmetric-ish. That's probably good enough. Don't be too much of a stickler on this. We want it to pass typically. And again, it's a small sample size, so it's not going to look normal, but we're hoping we can say the population is normal by looking at that. So let's see what they said. They said random sample, less than 10%, and the dot plot. So they drew the dot plot like we had on the calculator, and you can see that the dot shows strong skewness or outliers, and that's good enough to pass the test. No strong skewness, no outliers. If that's the case, it's plausible the population distribution is approximately normal. That's what we're kind of hoping for here. And so then we can kind of use our methods to go on with things. So now we do the do section, right? So the do section, you're going to take, so you're going to go, let me go back to the other screen because I think I had more information on it. Oh, it didn't have that much more in it, actually. Okay, so let's get our calculator out, and because we're going to need to do some number crunching here. So we probably have to do one variable stats on this. So hit the home key, go to a calculator page, not the scratch pad. Go menu 611, one variable stats, choose tension, and it gives you most of the stuff you're going to need here. So it gives you X bar. So remember the formula is X bar. So 306.22 plus or minus T critical value. So I didn't figure that out for this one, so I need to. So I think it was 90% confident. Let's see, 90%. So I'm going to go inverse T of 0.95 because there's 95% left, comma, I think it'd be 19 would be degrees of freedom. So we think that's 1.729 times standard deviation, which if we look back at our calculator, it should have the sample standard deviation. So that's SX right there is 36.2093, 36.2093 divided by square root of n, which is 20. So then you would type that into your calculator and get it that way. Also a really good idea to go ahead and do it in your calculator. So let's perform the interval in the calculator. So menu 6, got to be intervals, number 6. It's the T interval. This time we're choosing data. The name of the list, of course, was called tension, and it was 0.9, not 0.90. And we say OK. And it gives us the lower bound, which is 292. 0.32, comma the upper bound 320.32. And so that's the two numbers you have to have for the do section. I also think it's a really good idea to write degrees of freedom equals 20 minus 1 equals 19. Good communication there. I recommend doing that as well. But that's good. Okay, so the do section, let's see what if they did something pretty similar to we did. They got the same results. Very good. And so using technology, you get pretty much the same results. They even wrote with degrees of freedom. I like adding that to that. And so that now we say we are 90% confident the interval from 292.32 to 320.32 contains the true mean, not the true proportion, of the true mean tension of video screens produced that day, or something to that effect. Let's see what they said. Captures the true or the mean tension of all the screens produced that day. Oh, they added this. I like that move. They added the units, which is millivolts there, I think. So really good move. That's more context. Sometimes the rubrics, they really like when you include units on the numbers there. So really good move there. So the manufacturer's goal is to produce video screens with an average tension of 300 based on the interval. So where does 300 fall in that interval? So 300 is inside that interval. That's a plausible value. So based on that, is there convincing evidence? It's a plausible value. So we can't prove it doesn't meet the goal. In fact, it seems plausible that it is reaching the goal. So we can't prove it otherwise. Because 300 millivolts is within the plausible values, it's within the interval, there's not convincing evidence that video screens don't meet this manufacturer's goal. So they're doing a good job of doing this, evidently. For the do section, make sure to, again, include the lower bound and upper bound. I think degrees of freedom as well. And then the other sections you have to actually do. The calculator doesn't do it all for you. Just a couple practice problems, but we're basically done with the lesson. In the preceding example that Rob wrote are burritos one. So calculate a 90% confidence interval for this guy. So this is using stats. And so then you would get the interval like that using the do section. And then for this one, if you do that one, you could check all the conditions and do that one. So just more practice for you if you want to do a few more problems with that. And then just a follow-up question, if that's the interval, is there evidence that the target website has a fast load time on average this day? So yes, because all the values are less than 1, there's convincing evidence the website had fast load time. That's your lesson for today.